In this lesson, we are going to solve a simple problem on binary tree, which is also a famous programming interview question. And the problem is, given a binary tree, we need to check if the binary tree is a binary search tree or not. As we know, a binary tree is a tree in which each node can have at most 2 children. All these trees that I have drawn here are binary trees, but not all of them are binary search trees. Binary search tree, as we know, is a binary tree in which for each node, value of all the nodes in left subtree is lesser, and if we want to allow duplicates, we can say lesser or equal, and value of all the nodes in right subtree is greater. We can define binary search tree as a recursive structure like this. Elements in left subtree must be lesser or equal, and elements in right subtree must be greater. And this should be true for all nodes and not just the root node. So left and right subtrees should themselves also be binary search trees. Of these binary trees that I'm showing here, A and C are binary search trees, but B and D are not. In B, for the root node with value 10, we have 11 in its left subtree, which is greater than 10. And in a binary tree, for any node, all values in its left subtree must be lesser. In D, we are good for the root node. The value in root node is 5, and we have 1 in left subtree, which is lesser, and we have 8, 9, and 12 in right subtree, which are greater. So we are good for the root node, but for this node with value 8, we have 9 in its left. So this tree is not a binary search tree. So how should we go about solving this problem? Basically, I want to write a function that should take pointer or reference to root node of a binary tree as argument, and the function should return true if the binary tree is BST, false otherwise. This is how my method signature will look like in C++. In C, we do not have Boolean type, so return type here can be int. We can return 1 for true and 0 for false. I'll also write the definition of node here. For a binary tree, node would be a structure with 3 fields, 1 to store data and 2 to store addresses of left and right children. In my definition of node here, data type is integer, and we have 2 pointers to node to store addresses of left and right children. Okay, coming back to the problem. There are multiple approaches, and we are going to talk about all of them. The first approach that I'm going to talk about is easy to think of, but it's not so efficient. But let's discuss it anyway. We are saying that for a binary tree to be called binary search tree, it should have a recursive structure like this. For the root node, all the elements in left subtree must be lesser or equal, and all the elements in right subtree must be greater, and left and right subtrees should themselves also be binary search trees. So let's just check for all of this. I'm going to write a function named isSubTreeLesser that will take address of root node of a binary tree or subtree and an integer value as argument, and this function will return true if all the elements in the subtree are lesser than this value. And similarly, I'll write another function named isSubTreeGreater that will return true if all the elements in a subtree are greater than a given value. I have just declared these functions. I'll write body of these functions later. Let's come back to this function isBinarySearchTree. In this function, I'm going to say that if all elements in left subtree are lesser, and I'll verify this by making a call to isSubTreeLesser function, passing it address of left child of my current root. Left child would be the root of left subtree, and the data in root. This function call will return true if all the elements in left subtree would be lesser than the data in root. Now the next thing that I want to check for is if elements in right subtree are greater than the data in root or not. These two conditions are not sufficient. We also need to check if left and right subtrees are binary search trees or not. So I'll add 2 more conditions here. I have made a recursive call to isBinarySearchTree function passing it address of left child, and I have made another call passing address of right child. And if all these 4 function calls, isSubTreeLesser, isSubTreeGreater, and isBinarySearchTree for left and right subtrees return true, if all these 4 checks pass, then our tree is a binary search tree. We can return true, else we need to return false. There is only one thing that we are missing in this function now. We are missing the base case. If root is null, that is, if the tree or subtree is empty, we can return true. This is the base case for our recursion where we should stop. With this much of code, isBinary search tree function is complete. But let's also write its subtree lesser and its subtree greater functions because they're also part of our logic. This function has to be a generic function that should check if all the elements in a given tree are lesser than a given value or not. We will have to traverse the complete tree or subtree and see value in all the nodes and compare these values against this given integer. I'll first handle the base case in this function. If the tree is empty, we can return true. Else we need to check if the data in root is less than or equal to the given value. And we also need to recursively check if left and right subtrees of the current root have lesser value or not. So I'm adding two more conditions here. I'm making two recursive calls, one for the left subtree and another for the right subtree. If all these three conditions are true, then we are good, else we can return false. Its subtree creator function will be very similar. Instead of writing these two functions, its subtree lesser and its subtree creator, we could also do something like this. We could find the maximum in left subtree and compare it with the data in root. If maximum of a subtree is lesser, then all the elements are lesser, and similarly, if the minimum of a subtree is greater, all the elements are greater. For the right subtree, we could find the minimum. So instead of writing these two functions, its subtree lesser and its subtree greater, we could write something like find max and find min, and this would also fit. So this is our solution using one of the approaches. Let's quickly run this code on an example binary tree and see how it will execute. I have drawn a very simple binary tree here, which actually is a binary search tree. Let's assume some addresses for these nodes in the tree. Let's say the root node is at address 200, and I'll assume some random addresses for other nodes as well. To check if this binary tree is a binary search tree or not, we will make a call to isBinarySearchTree function. I'm writing IBST here as shortcut for isBinarySearchTree because I'm short of space here. So I'll make a call to this function, maybe from the main function, passing address 200, address of the root node. For this function call, address in this local variable, address collected in this local variable root, will be 200. Root is not null. Null is only a macro for address 0. For this call, root is not null, so we will not return true at this line. We will go to the next if. Now here we will make a call to isSubtree lesser function. Arguments passed will be address of left child, which is 150, and 7, the data in node at 200. Execution of the calling function will pause and will resume only after the called function returns. Now in this call to isSubtree lesser, root is not null, so we will not return true at first line. We will go to the next if. Now here the first condition is if data in root, and the root this time is 150, because this call is for this left subtree, and for this left subtree address of root is 150. Data in root is 4, which is lesser than 7. So the first condition is true, and we can go to the second condition, which is a recursive call. This call will pause and we will go to the next call. Here once again the data in node at 180, 1 is lesser than 7. So first condition is true and we will make a recursive call. Left subtree for node at 180 is null. There is no left child, so we will return at first line. Root is null this time. This particular call will simply return true. Now in this previous call, when root is 180, second condition for if is also true, so we will make another call for right subtree. Once again address passed will be 0 and we will simply return true. And now for this call is subtree lesser 187. All three conditions are true, so this guy can also return true. And now this call ISL 157 will resume. Now this guy will make a recursive call for the right subtree, and this guy after everything will also return true. Now for this call, because all three conditions in the if statement are true, this guy will also return true. and now is binary search tree function will resume. For this call, we have evaluated the first condition. We have got true. Now this guy will make another call to its subtree getter, passing address of right child and value 7. This guy, after everything, will return true. And now we will have two recursive calls to check if left and right subtrees are binary search trees or not. We will first have a call for the left subtree. The execution will go on like this, but I want you to see something. In each call to binary search tree function, we are comparing the data in root with all the elements in left subtree and then all the elements in right subtree. This example tree could be really large. Then in that case, in the first call to isBinary search tree, for this complete tree, we would recursively traverse this whole left subtree to see whether all the values in this subtree are less than 7 or not. And then we will traverse all nodes in this right subtree to see if values are greater than 7 or not. And then in next call to isBinary search tree, when we would be validating whether this particular subtree is BST or not, we would recursively traverse this subtree if values are lesser than 4 or not, and this subtree to see if values are greater than 4 or not. So all in all, during this whole process, there will be a lot of traversal. Data in nodes will be read and compared multiple times. If you can see, all nodes in this particular subtree will be traversed once in call to isBinary search tree for 200, when we will compare value in these nodes with 7, and then these nodes will once again be traversed in call to isBinary search tree for 150, when they will be compared with 4. They will be traversed in call to its subtree lesser. All in all, these two functions, its subtree lesser and its subtree greater, are very expensive. For each node, we are looking at all nodes in its subtrees. There is an efficient solution in which we do not need to compare data in a node with data in all nodes in its subtrees. And let's see what the solution is. What we can do is we can define a permissible range for each node, and data in that node must be in that range. We can start at the root node with range -infinity to infinity, because for the root node there is no upper and lower limit. And now as we are traversing, we can set a range for other nodes. When we are going left, we need to reset the upper bound. So for this node at 150, data has to be between -infinity and 7. Data in left child cannot be greater than data in root. If we are going right, we need to set the lower bound. For this node at 300, range would be 7 to infinity. 7 is not included in the range. Data has to be strictly greater than 7. For this node at 180, the range will be -infinity to 4. For this node with value 6, lower bound will be 4 and upper bound would be 7. Now my code will go like this. My function isBinary search tree will take two more arguments. An integer to mark the lower bound or min value, and another integer to mark the upper bound or max value. And now instead of checking whether all the elements in left subtree are lesser than the data in root and all the elements in right subtree are greater than the data in root or not, we will simply check whether data in root is in this range or not. So I'll get rid of these two function calls, its subtree lesser and its subtree greater, which are really expensive, and I'll add these two conditions. Data in root must be greater than min value and data in root must be less than max value. These two checks will take constant time. Its subtree lesser and its subtree greater functions were not taking constant time. Running time for them was proportional to number of nodes in the subtree. Okay, now these two recursive calls should also have two more arguments. For the left child, lower bound will not change. Upper bound will be the data in current node. And for the right child, upper bound will not change and lower bound will be the data in current node. This recursion looks good to me. We already have the base case written. The only thing is that the caller of isBinary search tree function may only want to pass the address of root node. So what we can do is, instead of naming this function isBinary search tree, we can name this function as a utility function like isBSTUtil, and we can have another function named isBinary search tree in which we can take only the address of root node, and this function can call isBSTUtil function passing address of root minimum possible value in integer variable for minus infinity and maximum possible value in integer variable for plus infinity. Int min and int max here are macros for minimum and maximum possible values in int. So this is our solution using second approach, which is quite efficient. In this recursion, we will go to each node once, and at each node we will take constant time to see whether data in that node is in a defined range or not. Time complexity would be big O of n, where n is number of nodes in the binary tree. For the previous algorithm, time complexity was big O of n square. One more thing, in this code I have not handled the case that binary search tree can have duplicates. I'm saying that elements in left subtree must be strictly lesser and elements in right subtree must be strictly greater. I'll leave it for you to see how you will allow duplicates. There is another solution to this problem. You can perform in-order traversal of binary tree, and if the tree is binary search tree, you would read the data in sorted order. In-order traversal of a binary search tree gives a sorted list. You can do some hack while performing in-order traversal and check if you are getting the elements in sorted order or not. During the whole traversal, you only need to keep track of previously read node, and at any time data in a node that you are reading must be greater than data in previously read node. Try implementing this solution, it will be interesting. Okay, I'll stop here now. In coming lessons we will discuss some more problems on binary tree. Thanks for watching.